In this video, we're going to be doing two more U substitution types of problems. U substitution, again, part of the recognition is, does this have a chain rule feel to it? So here's kind of an inside and here's an outside, here's an inside, here's an outside. So that's part of it. But I also, if you look back at these other two examples, we have this inside part, and what I'm looking for is the derivative of the inside. Does it have that also represented in the problem? And I'm not worried about the two, I'm worried about the power. If I do a derivative of a quadratic, I get a linear. If I do a derivative of x cubed, I get an x squared. So that piece is kind of the second piece to this that we want to make sure that we can use chain rule. Does it have U substitution, which meant it came from a chain rule? Does it have this inside piece? And then does the derivative of the inside piece have this feel to it? If it does, perfect. And that inside piece is your U. So for me on this one, my inside piece would be this quadratic. So if there's any chance that U substitution is going to work, that's my only option. And then my du is 2x plus 5 dx, which perfectly sits right there. Great. So I can take these two pieces and replace them with du. I can take this piece and replace it with u and rewrite it. So this all becomes u to the fifth, and these two pieces become du. And that's what I'm doing my antiderivative of. So I will add my power, divide by my power, and then just sub things back in. So I'll clean this up as a 1/6. And then this is my u, so x squared plus 5x plus 10 to the sixth power plus c. All right, so same kind of a situation on this one is I'm looking for, does it have that chain rule feel where there's an inside and an outside? Yes. And if I do the derivative of an x to the fifth, do I get an x to the fourth? Yes. So both of those pieces are lining up, and this is definitely a u substitution kind of a problem. So we'll let our u equal this inside piece, x to the fifth plus 2. And then I'm going to rewrite all these pieces. So first off, I don't like the fraction idea, so I can pull this x to the fourth off. I want to make this more antiderivative friendly, which means let's avoid fractions. So let's take that piece and let's write it as a negative exponent. So -5. I'll pull the x to the fourth off and just kind of put it next to the dx. All right, and so that does a couple things for me. It makes it ready to do my antiderivative just because it's more antiderivative slash derivative friendly. And then this piece right here, when I do my derivative of u, I will get a 5x to the fourth dx. Perfect. There's my x to the fourth dx. Let's just isolate this piece and get the 5 out of there. So that's a 1/5 du equals x to the fourth dx. And there's my perfect substitution. So my 1/5, I don't need it to be part of my integral at all. We'll just mix it back at the end. This is u to the -5th, and this is part of my 1/5 du substitution. All right, I'm ready to finish. So this is, we'll add a power, divide by that power. So we still have our 1/5. We add our power, which is -4, divide by that power, and then plus c. So this all simplifies together to a -1/20th. And then this becomes whatever our u was, so x to the fifth plus 2 to the -4 plus c. All right, so similar to this radical problem, it depends on, are they okay with negative exponents being your final solution? Are they okay with fractional exponents, or do you need to rewrite it as radicals? Do we need to rewrite this so it's not a negative exponent? Sure. So if this is okay, then you're done. But if you know that you need to not have negative exponents, that's fine. So let's pull this all together where we're going to have a fraction. I'll apply the negative onto the top, and then it's 20. And then I'm bringing this piece down to join the denominator. X to the fifth plus 2. Now to a positive fourth power, and then plus c. So it just kind of depends on how it needs to be finalized. So maybe this might be okay, or that one might be okay.